I mean, usually when people picture the intersection of data and science, the mental image is just overwhelmingly
Oh,
sterile.
entirely. It's this vision of pristine objectivity, right?
Exactly. Like a researcher in a white coat draws a water sample, slots a vial into some highly calibrated machine, it whirs, and then this perfectly definitive number just appears on a spreadsheet.
Pure, unadulterated facts.
Right. Just sitting there in these clean rows and clean columns, totally ready to be fed into an algorithm that will, reveal the absolute truth of the physical world.
Yeah, it's a very comforting piece of modern mythology. We desperately want to believe that the CSV file on our monitor is just a flawless one-to-one mirror of reality.
But the moment you actually step into the field of environmental science, right,
Yeah.
and specifically the reality of water quality monitoring, that sterile laboratory just completely shatters.
Oh, it shatters immediately. The reality is that the actual physical sensors out in the river have literal algae growing across their optical lenses.
Yeah, or the batteries are dying because it dropped below freezing the night before.
Exactly. And because of that, the spreadsheets are just a chaotic, deeply structural mess. We aren't looking at a pristine mirror of the environment at all. We are looking at a landscape that is profoundly muddy.
Diagnostic muddy waters, basically.
That's a great way to put it. The raw data we extract from the physical environment is almost never a clean reflection. It is heavily refracted through, well, the limitations of the instruments, the chaos of the weather, and, frankly, the quirks of the humans recording it.
Which brings us to the mission for today's deep dive. Because this reality strikes at the very core of what we are unpacking today.
It really does.
We are looking at this highly specialized facilitator guide, and it is focused specifically on data preprocessing, harmonization, and feature engineering for environmental data sets.
And its central thesis is basically designed to completely shatter that illusion of the clean data set.
Yeah, the claim the source material makes is actually quite provocative. I mean, in data science, people generally treat preprocessing as just, well, as janitorial work, right?
Right, like it's purely cosmetic.
Exactly. You're just sweeping the floor, maybe deleting a few stray commas, making sure the date format matches so your Python script doesn't just throw a fatal error when you hit run.
But this guide argues something radically different. It argues that preprocessing is actually the single most dangerous part of the entire scientific method.
Wait, the most dangerous?
Yes, because it is the exact threshold where a physical measurement stops being a record of the real world and is actively transformed into a mathematical assumption.
Oh, wow.
Yeah. I mean, the broader cultural obsession right now is entirely fixated on the modeling place.
Right. Everyone's obsessed with the AI.
Exactly. We scrutinize the architecture of the neural network, the hyperparameters, the sheer computational power. But the guide forces us to realize that the vast majority of statistical bias and, frankly, the most catastrophic scientific errors, they enter the process long before the model ever compiles.
The bias is permanently baked in during preprocessing.
Sure.
The analogy that came to mind when I was reading this is a crime scene. Imagine a detective walking into a room. There's mud tracked across the carpet, a shattered lamp in the corner, and a faint, partial footprint near the window.
Okay, I like this.
Right. So pre-processing raw data is not just sweeping the floor before the forensic investigators, which would be our statistical models, arrive to solve the case.
No, not at all.
Pre-processing is the highly subjective act of deciding which footprints matter and which ones get scrubbed away with bleach before the detective is even allowed into the room.
That is exactly it, because if you scrub away the wrong footprint just because it looked a bit too messy, or maybe it didn't fit your initial theory,
The detective is going to perform a flawless analysis of the remaining evidence.
right, the model will converge perfectly, the mathematics will be completely sound, and the resulting conclusion will point to the entirely wrong suspect. The algorithm worked, but the science is a fiction.
So, to understand exactly how that bias sneaks into the mathematics, we have to look at the structural state of the data when it first arrives from the field.
Yes, and the overarching rule the guide establishes immediately is raw does not equal ready.
It details how water quality data arrives with deep, deep structural damage. Like we were talking about numerical values formatted as text strings,
Units of measurement typed directly into the cells alongside the numbers.
dates fused with spatial coordinates, and replicates that have just been arbitrarily averaged together.
And we really need to be very clear about the nature of this brokenness.
Yeah.
These aren't software glitches.
Right, it's not like the database corrupted.
No, they are artifacts of a messy physical reality. Think about the field technician. They are standing waist deep in a fast-moving river during a torrential downpour, trying to log a turbidity sample.
Sounds miserable, honestly.
It is, and they are writing Site A, heavy rain, less than 1 μ.01, into a waterproof notebook with a pencil. And then days later, a tired graduate student is manually typing that exact string of text into Excel.
So the structural mess of the data is actually a vital historical record of the human and environmental constraints under which it was gathered in the first place.
Exactly, which is why you can't just blindly delete it.
Okay, let's unpack this concept of schema repair, because this is where the guide demands we stop acting like janitors and start acting like data architects.
Yes, the guide asks a brilliant question here. What happens when a single column contains far too much physical reality?
It gives a classic, universally recognizable example. You look at a column labeled Sample ID, right? And one of the rows contains the string 2023-0914 underscore site IDO3 underscore REP2.
Ah, the compound string. It is the absolute bane of environmental data sets.
To a database, that's just a unique string of characters, right?
Right, it has no intrinsic meaning beyond its distinctness from the next string.
Yeah.
But to a physical scientist, that single cell is effectively a compressed spreadsheet.
It holds three entirely distinct dimensions of the experiment.
Yes, the temporal dimension of the date, the spatial dimension of Site 03, and the methodological dimension of it being the second replicate sample.
So if a data scientist looks at that and just says, well, it's just a unique identifier, I'll leave it as is, or maybe I'll just drop it entirely because my model doesn't need an ID column.
They are intellectually paralyzing the entire analysis.
Because the model has absolutely no way to know that the first part of that string is a timestamp. So you can't model seasonality.
Right, and it doesn't know that Site 03 is a physical place that exists upstream of Site 04, so you cannot test for spatial distribution or point source pollution.
The physical dimensions of the river are locked inside a text string that the algorithm treats as a literal barcode.
Schema repair in this context is the act of forcefully extracting those dimensions. You have to parse that string into three distinct columns: date, location, and replicate number.
Because if you feed the raw compound string into a tree-based machine learning model, what happens?
The algorithm will treat every single unique timestamp location replicate combination as a completely independent category. It will just explode the dimensionality of your dataset while learning absolutely nothing about the underlying physics.
But by splitting the columns, you are handing the geometry of the physical world back to the algorithm. You are teaching it how time and space actually operate in your specific dataset.
Precisely. It's foundational.
This actually brings up another schema repair practice the guide heavily critiques, and I'll admit it's one that really challenged my own assumptions.
Oh, the replicate averaging.
Yes, it's this incredibly common practice of averaging replicate samples. Like, let's say the lab analyzes the exact same vial of river water twice, just to be thorough.
A standard quality control step, sure.
Right. And they get a pH reading of 7.1 and then a second reading of 7.3. The standard instinct, and honestly what is often taught as best practice to make the data quote-unquote cleaner, is to average those together.
Right, you create a final column that just says 7.2, and you delete the original readings.
But the guide views this as a structural error. Wait, isn't averaging replicates just standard practice to get a cleaner, more reliable number? Why is the source warning against this?
Because it is a destruction of vital information. When you average those two replicates and delete the originals, mathematically, yes, you have calculated the mean. But scientifically, you have permanently erased the record of measurement uncertainty.
Oh, you scrubbed the footprint.
Precisely. Let's trace the actual mechanics of that destruction. In scenario A, your two readings are 7.1 and 7.3. The average is 7.2. The variance is incredibly small.
So the instrument is stable, the sample is well mixed, and we have high confidence in that number.
Exactly. Now consider scenario B. Your two readings are 6.0 and 8.4.
Whoa. Okay, mathematically, the average is still exactly 7.2.
But the physical reality is completely different. A pH of 6 is acidic, a pH of 8.4 is highly alkaline. If the exact same vial of water is giving you both of those numbers back to back...
Either the water chemistry is highly volatile, or more likely, your pH probe is just mechanically failing.
Exactly. But if you only pass the average value of 7.2 to your predictive model, the model receives the exact same input for both scenario A and scenario B.
It fundamentally assumes that in both cases, the instrument was perfectly stable, and the physical state of the river was unambiguously 7.2.
You have blinded the algorithm to the variance. When the model eventually makes a prediction, it will do so with a false manufactured confidence because you actively hid the instrument's disagreement from it.
Preprocessing must be about restructuring the data so the algorithm can perceive it without ever inventing certainty that didn't exist in the physical world.
That's the golden rule right there.
So once we've mapped out these structural dimensions, splitting the compound strings, preserving our replicates, stopping this habit of premature averaging, we inevitably run headfirst into the next massive hurdle in any environmental data set,
The empty spaces.
the blank cells, and the wildly dangerous numbers we try to shove into those empty spaces just to force our code to compile.
What's fascinating here is how the architecture of modern software actually tricks us. In Excel, or in a pandas data frame in Python, a missing value looks identical no matter where it appears.
Right, it's a null, an NA, a blank cell.
The software renders absence uniformly, but the guide emphatically states, missing does not equal missing.
A blank cell isn't just a void, it has a specific origin story. And the guide breaks down 3 distinct real-world cases for why a water quality measurement might be missing.
Right. Case 1 is missing due to failure.
Like a tree branch falls and crushes the sensor array, or the battery dies. The cellular modem loses connection. The data is gone, but its absence has absolutely nothing to do with the actual chemistry or flow of the water.
In statistical terms, this is often treated as missing completely at random. The probability of the data point being absent is independent of the true value of the water quality at that moment. The river didn't cause the tree branch to fall.
But case 2 flips that entirely. Missing conditional on conditions.
Yes. This is where the physical environment actively causes the absence of the data.
The example given is extreme turbidity during a monsoon. The river floods, the water fills with thick, opaque mud, and the optical dissolved oxygen sensor is completely blinded by the sediment.
It just stops recording. So the data isn't missing randomly. It is missing specifically because the physical system entered an extreme state.
Think about the mathematical consequence of treating case 2 like case 1. If a data scientist looks at those blank cells and says, well, my algorithm can't handle missing data, so I'll just drop those rows.
They are not just cleaning the data set, they are systematically deleting the most extreme, highly energetic events from the historical record.
They are effectively lobotomizing the model. If you use that pruned dataset to train a predictive model for flood risk or infrastructure stress, the model will output results that imply monsoons simply do not exist.
Because it has never seen one. You deleted the evidence of its occurrence just because the sensor couldn't handle the mud.
Which is terrifying if an engineer relies on that model to determine how much concrete to pour for a new dam.
You engineer a catastrophic failure by prioritizing a complete spreadsheet over a truthful one.
Precisely. And this leads us directly into case 3, which the guide treats as the most pervasive and dangerous trap in environmental preprocessing. Missing because a value is below detection. The below detection limit, or BDL.
This specific type of missingness corrupts more environmental models than perhaps any other error because the physical mechanics of the instrumentation are fundamentally misunderstood.
A data set tracking nitrate concentrations in a river. You read down the column, 0.32 milligrams per liter, then 1.1.
And then you hit a cell that just says less than 0.05.
And the next cell says ND for non-detect. The guide explicitly warns, less than 0.05 milligrams per liter does not equal 0, and it does not equal missing.
We have to look at the physics of a mass spectrometer or a colorimetric assay and understand why. Every physical instrument has a floor limit of detection.
Right, it can only see so much.
Exactly. As the concentration of nitrate in the water sample drops, the signal the instrument receives gets fainter and fainter until it begins to drown in the baseline electrical noise of the machine itself.
So when the lab reports less than 0.05, they're not saying there is 0 nitrate.
No, they are reporting a state of bounded uncertainty.
Bounded uncertainty. The instrument is basically saying, I ran the chemistry, the molecules are likely in there, but the concentration is so diluted that the signal-to-noise ratio has degraded past my ability to give you a definitive integer.
Yes. I can only mathematically guarantee that the true concentration exists somewhere in the physical space between absolute 0 and 0.049.
Okay, so what happens when the data scientist, sitting in an office hundreds of miles from the river, realizes their linear regression model will throw a fatal type error if it tries to multiply the string less than 0.05 by a coefficient.
Well, the most common, deeply flawed instinct is to do a bulk find and replace, turning every less than sign and every ND into a hard zero.
Because 0 is a number, the code compiles, and the problem seems solved.
But by replacing that bounded uncertainty with a zero, you are forcing the data to make an absolute physical claim. You are asserting with complete mathematical confidence that there are precisely 0 molecules of nitrate in that liter of water.
And the instrument never claimed that. The chemistry doesn't support that.
Yeah.
You are effectively putting words in the sensor's mouth.
Let's trace the impact of that false zero down into the mathematics of the model. If you have a data set where, say, 30% of the readings are below detection,
Which is pretty common, right?
very common, and you convert them all to hard zeros, you aggressively drag the mean of your entire data set downward. You artificially reduce the variance.
So if your model is trying to learn the baseline nutrient load of that river, you have just taught it that the river is significantly more pristine than it actually is.
Exactly. And when a real pollution event occurs, the model's baseline is so artificially depressed that the spike will look mathematically impossible, or it will wildly miscalculate the required recovery time.
It's like using a camera to count wildlife in a forest. You take a photo of a clearing at dusk. The lighting is terrible, the resolution is low, and there's a blurry patch near the tree line.
I love this analogy.
If you enter into your spreadsheet, there are exactly 0 deer in this photo, you are lying. The honest, scientifically rigorous answer is, the number of deer is less than or equal to the resolution required for my camera sensor to detect them.
The camera sensor resolution is the exact analog to the chemical assay's limit of detection. You cannot assert a negative just because your tool lacks the sensitivity to see the positive.
So the dilemma then becomes purely practical. I mean, if I can't use 0 because it's a physical lie, and I can't leave the string because the machine learning algorithm will violently reject it, how do we process this without corrupting the math?
Well, the guide outlines specific statistically defensible treatments. The first is exploratory substitution, which is acceptable if you only need to understand the rough shape of the data's distribution.
Okay, what does that look like?
Instead of substituting 0, you use a fractional substitute of the limit of detection. The most common heuristics are dividing the LOD by 2 or dividing it by the square root of 2.
So if the limit is 0.05, dividing by 2 gives you 0.025. You replace the string with that number.
Right. The physical assumption you are making there is that the true unmeasured value is likely hovering somewhere in the middle or lower half of that bounded uncertainty range.
It is an estimation, yes, but it is orders of magnitude more honest than asserting a hard 0.
Exactly. However, the guide pushes for a much more robust, architecturally sound method for predictive modeling, the creation of a binary indicator flag.
Let's walk through the mechanics of that. How does the flag system actually work in the data frame?
You preserve the original column, perhaps applying that fractional substitution so the math can run. But crucially, you engineer a brand new column adjacent to it.
Okay.
Let's name it nitrate_censored. For every single row where the original instrument reported a value below the detection limit, you place a 1 in this new column. For every row where the instrument got a clean, high confidence reading, you place a 0.
You are building a parallel track of metadata. You are explicitly passing a mathematical flag to the algorithm that says, warning, the number sitting next to this flag is not a definitive measurement. It is an artifact of the instrument's limitation.
Adjust your weights accordingly. Yes. Think about how a tree-based algorithm, like an XGBoost model, processes that flag.
Right, because it splits data.
Exactly. When it builds a decision tree, it can literally split the data on that nitrate_censored column. It isolates all the uncertain, low-concentration readings into one branch and all the high-confidence readings into another.
You have successfully encoded the physical limitations of the mass spectrometer directly into the logic of the artificial intelligence.
It can now learn the difference between a pristine river and a blind sensor.
Here's where it gets really interesting. Because we've mapped out the physical dimensions by fixing the schema, we've stopped lying to the algorithm about what the blank spaces and the less than signs mean. Now we reach the phase where we have to actively build the inputs that the model will learn from. This is feature engineering. And the guide issues a massive warning here.
Oh, a huge warning.
Because in a lot of tech sectors, feature engineering is basically an automated playground. You let a script multiply, divide, and square hundreds of columns against each other just to see which random combination boosts the accuracy metric by 0.5%.
The brute force approach, throwing mathematical spaghetti at the wall.
But the guide establishes a hard, non-negotiable boundary for environmental data. It states, a feature is only scientifically valid if it explicitly encodes a physical hypothesis about the system.
If you cannot look at the math to articulate the physical, real-world mechanism it represents, you are forbidden from creating it.
An environmental model is not an excuse to play number games.
And this is the difference between a statistician and an environmental data scientist. The architecture of the features must mirror the physical architecture of the watershed.
Right, because if you just unleash an automated polynomial feature generator on a river data set, the algorithm will invariably find patterns, right?
It will find a highly predictive correlation between the square root of the turbidity and the inverse of the battery voltage of a sensor at 3.0 p.m. The math will check out. The accuracy score will climb.
But the result is a hallucination. It has learned the specific random noise of your hardware, not the dynamics of the water.
Precisely.
The appendix of this guide provides extensive, highly detailed examples of what a physically grounded feature actually looks like. And I want to examine these because the translation from environmental theory to Python code is fascinating.
Just do it.
Let's start with ratios. The specific example is creating a new feature by taking total dissolved solids, TDS, and dividing it by conductivity. What is the physical hypothesis behind that division?
Well, total dissolved solids is a measure of the actual mass of material, so minerals, salts, metals, dissolved in a volume of water. Conductivity measures how well that same water conducts an electrical current, which is driven by those exact same dissolved ions.
Physically, these two phenomena are inextricably linked. They should move in tandem.
Exactly. By engineering a feature that is the ratio of TDS to conductivity, you are mathematically encoding an ionic consistency check.
You are teaching the model the basic laws of physical chemistry. The hypothesis is that the fundamental relationship between the mass of the solids and their electrical charge should remain relatively stable.
Right. If that engineered ratio suddenly violently spikes or collapses, the model isn't just seeing a change in water, it is detecting either a radical shift in the specific types of ions in the river.
Like perhaps an industrial chemical spill that alters conductivity without adding mass?
Yes. Or it is detecting that one of the two physical sensors has completely broken calibration. The ratio forces the algorithm to evaluate the two variables against each other rather than as isolated streams of numbers.
Let's look at logarithmic transforms. You take the concentration of a nutrient, like nitrate or phosphorus, and you apply a log function to it. You see this constantly in environmental papers, but the justification is almost always we log transform the data to normalize the distribution.
Which just sounds like trying to make the bell curve look pretty for publication.
Right.
Doing it purely for aesthetic normalization is mathematical vanity, and it often obscures the truth. The genuine scientific justification for a logarithmic transform is the hypothesis that the variability in the physical system is multiplicative rather than additive.
Okay, let's trace that out. What is the physical difference between additive and multiplicative variance in a river?
If variance is additive, a change from 1 milligram of nitrate to 10 milligrams has the same physical impact as a change from 100 to 109.
An addition of 9 units is 9 units, regardless of the baseline.
But biological systems rarely operate like that. Algae, for example, grows exponentially. It responds to relative changes, not absolute ones.
Right, a shift from 1 milligram to 10 milligrams represents a tenfold increase in available food.
Exactly. It might trigger a massive ecosystem-choking algae bloom. But a shift from 100 to 109 is biologically negligible. The system is already saturated.
So by applying the log transform, you are literally translating the raw milligrams into the mathematical language that the algae actually experiences.
Yeah.
You are scaling the data to match the biological reality of the watershed.
Precisely. You are telling the model that relative magnitude is the true driver of the system, though we must link this back to our previous discussion on missing data.
Oh, right. Because you mathematically cannot take the log of 0.
You cannot. If you lazily replaced all your below detection limit values with hard zeros during preprocessing, the moment you attempt to execute this log transform, the function will evaluate to negative infinity.
Your code will violently crash. Or worse, it will quietly corrupt the entire data frame with uncomputable values, destroying the model's weight distribution.
The order of operations handling the physical limits of the sensor before attempting to model the biology is absolute.
The next example is temporal or rolling metrics. The guide suggests engineering a feature like a 7-day rolling mean of turbidity. So for every row, you calculate the average murkiness of the water over the preceding 168 hours. The obvious question is, why 7 days? Why not a 3-day window? Or a nice round 30-day window?
Because the time window cannot be arbitrary. It must represent a measurable physical property of that specific environment. In hydrodynamics, this is often the hydraulic residence time.
Meaning the actual physical amount of time it takes for a specific drop of water to enter a lake or a river segment, travel through it, and exit downstream.
Yes. The scientific hypothesis encoded in a rolling mean is that the aquatic system possesses temporal memory.
Temporal memory. I like that.
The physical state of the river today is not solely dictated by today's rainfall. It is heavily influenced by the sediment that was washed into the channel 4 days ago, which is still slowly grinding its way downstream.
So by engineering a 7-day rolling mean, you are explicitly teaching the algorithm the physical memory capacity of that specific watershed.
Right. Think about the consequences of getting that window wrong. Let's say you're modeling a flash flood-prone urban creek. The water hits the concrete, blasts through the channel, and drains into the ocean in 12 hours.
So the residence time is half a day.
If you apply a 30-day rolling mean to that data set, you are forcing the model to continuously analyze the memory of water that left the system 4 weeks ago. You are feeding the algorithm ghost data.
The model will expect the creek to be muddy because it rained 20 days ago, completely failing to understand that the system flushed itself entirely in an afternoon.
You've mismatched the mathematics to the physics. The rolling window must mirror the flow rate.
Let's move to categorical encoding. The example the guide provides is taking the physical position of the monitoring sites along a river upstream, midstream, downstream, and numerically encoding them as 1, 2, and 3.
On the surface, this just looks like turning words into numbers so the code doesn't crash.
It accomplishes that, but the physical hypothesis is far deeper. By mapping upstream to 1, midstream to 2, and downstream to 3, you are asserting an ordinal relationship.
Yeah.
You are mathematically encoding the physical reality of gravity, elevation, and flow direction into a single digit.
Yes. Because 2 is mathematically between 1 and 3, you are teaching the model that the midstream site physically exists between the other two.
If a massive spike in agricultural runoff hits site 1, the model, because of that ordinal encoding, knows to look for the resulting wave at site 2 before it ever reaches site 3.
If you had just used random category codes, like assigning upstream as 99 and downstream as 4, the algorithm would have no concept that water flows downhill.
You'd be asking the model to learn the laws of physics from scratch, using only variance, rather than providing the topographic architecture up front.
It's just so inefficient and error-prone.
Okay, here is an example that seems incredibly risky. Detrending. The guide details the process of removing long-term drift from a sensor.
Very common, but yes, very risky.
Let's say you have a conductivity sensor submerged in a river for an entire year. Slowly, over the months, biofouling occurs. Algae and mineral scale build up on the electrical prongs. As a result, the sensor's baseline readings artificially creep higher and higher day by day.
Right. So detrending is the mathematical act of identifying that upward slope and flattening it back out, subtracting the drift from the data.
It is a powerful, highly necessary tool for mitigating mechanical noise. But the danger is immense because applying a detrending function fundamentally assumes that, for an absolute fact, that the upward slope is entirely an artifact of the machine failing and not a signal from the physical world changing.
Exactly. Let's trace out how that goes wrong. Imagine it's not algae on the sensor. Imagine the monitoring site is located downstream of a rapidly expanding suburban development.
Okay.
Throughout the winter, the town is heavily salting the newly paved roads. Every time the snow melts, more and more chloride washes into the river. The true physical conductivity of the water is steadily rising over the course of the year.
Oh, wow. If the data scientist sits in their office, looks at that upward sloping line on a graph, assumes it's just standard sensor drift, and applies a detrending algorithm.
They have just mathematically erased the ecological impact of the entire suburban development.
They have sanitized the data set to the point of absolute blindness. The model will analyze the detrended data and conclude that the river's salinity is perfectly stable, entirely missing a critical, slow-moving infrastructure crisis.
Which is why the guide insists that feature engineering requires intimate domain knowledge. You cannot detrend a line without physically inspecting the watershed, or at least cross-referencing the maintenance logs of the sensor to confirm biofouling actually occurred.
That brings us to the final feature engineering example, and the one that requires the deepest physical context,
Hmm.
interaction features.
This is a great one.
The guide suggests multiplying two entirely distinct columns together. The example is rainfall multiplied by urban fraction. You take the inches of rain that fell, and you multiply by the percentage of the watershed that is covered in impermeable surfaces like concrete and asphalt.
The hypothesis being mathematically formalized here is conditional causality.
Conditional causality.
Yes, the physical impact of the primary variable, the rainfall, is entirely dictated by the context of the secondary variable, the land use.
Consider the physical mechanics of a rainstorm. If 2 inches of rain fall on an undisturbed, dense, old-growth forest, the canopy breaks the impact. The leaf litter acts as a sponge.
The root systems channel the water deep into the soil.
Exactly. The river nearby barely rises, and the water stays crystal clear. The physical system absorbs the energy.
But if those exact same 2 inches of rain fall on a sprawling landscape of shopping mall parking lots and concrete highways, none of it is absorbed.
Right. The water instantly sheets off the asphalt, violently washing a thick layer of motor oil, heavy metals, and tire dust directly into the storm drains, resulting in a massive, toxic flash flood in the receiving river.
So if you only provide the algorithm with a single column for rainfall, it will analyze the historical data and become hopelessly confused.
It will see that sometimes 2 inches of rain does absolutely nothing, and sometimes 2 inches of rain causes a catastrophic toxic spike. It will average those outcomes together and become terrible at predicting both.
By explicitly engineering the interaction feature, creating a new column, that is, rainfall times open fraction, you are handing the model the physical key to the puzzle.
You are mathematically teaching it that the volume of the rain is irrelevant without the context of what the rain is hitting.
You provide the neural network or the random forest with the exact geometric relationship it needs to differentiate between a sponge and a slide.
I mean, theoretically, an immensely deep neural network might eventually deduce that interaction on its own, given millions of rows of data, right?
Theoretically, yes. But environmental data sets are notoriously small and sparsely sampled. We do not have the luxury of letting the algorithm guess the physics. We must hard code the conditional causality into the features.
So we have repaired the broken schema. We have mapped the limits of our instruments. We have built these elegant mathematical features that encode the physics, the memory, and the topography of the watershed.
Our single spreadsheet is finally a robust reflection of reality.
But environmental science does not occur in a vacuum. To build a true predictive model, you almost always have to look beyond your own sensors.
You have to pull in weather data from a meteorological agency or agricultural land use data from a satellite or historical lab results from a different university.
You have to combine data sets. And according to the guide, this brings us to harmonization and dataset fusion.
This is the crucible. Combining distinct data sets is where the most silent, invisible, and catastrophic corruption of scientific data occurs.
It begins with the fundamental requirement of harmonization. Two numbers, regardless of how cleanly they are formatted, are only comparable if their units, their chemical calibration, and their operational context align perfectly.
The guide offers a harrowing example of chemical harmonization regarding nitrate. It points out the difference between measuring milligrams per liter as NO3 minus versus milligrams per liter as N.
Milligrams per liter as nitrate versus milligrams per liter as nitrogen. To a software engineer writing a merge script or even a junior analyst, those sound like semantic variations of the exact same thing.
The column headers both contain the word nitrate. They sound identical, but chemically they represent radically different masses.
Right, because the nitrate molecule is composed of 1 nitrogen atom and 3 oxygen atoms.
And oxygen is heavy. If lab A is reporting milligrams per liter as nitrate, they are weighing the entire molecule. If lab B is reporting milligrams per liter as nitrogen, they are mathematically stripping away the oxygen and only reporting the mass of the single nitrogen atom.
And the weight ratio between the two is roughly 4.4 to 1.
Trace the destruction that causes. If you pull 10 years of historical data from Lab A and join it to 5 years of recent data from Lab B, and you just blindly paste them into the same column because the labels look similar,
You have just created a completely fictional environmental crisis.
the model will look at that combined column and observe what appears to be a 400% collapse in nutrient levels the exact month Lab B took over the contract.
The algorithm will fundamentally believe the ecosystem underwent a massive, unprecedented shift. Papers might be published theorizing about the sudden disappearance of the nutrients.
But the river never changed. Only the accounting method changed.
It's the environmental equivalent of merging a spreadsheet of Japanese yen with a spreadsheet of US dollars and treating them all as a single currency.
That's exactly what it is. The math executes perfectly, but the financial reality is completely hallucinated.
Which brings us to the concept of batch effects. The guide states emphatically, batch effects are not statistical noise. They are structure-induced by the measurement process itself.
Yes.
How does that manifest in the physical environment?
Imagine a long-term ecological study spanning 5 years. Halfway through year 3, the principal investigator secures a new grant and upgrades all the field sensors. They pull out the old optical turbidity probes and replace them with a brand new, highly sensitive laser scattering brand.
Okay, but the physical location hasn't moved an inch.
Right. But the mechanical eye looking at the water has fundamentally changed. Even with perfect calibration, that new laser sensor is going to read the baseline scatter of the water slightly differently than the old optical probe.
There will be a minute, persistent shift in the baseline numbers.
If you do not explicitly document this physical intervention in the dataset by introducing a batch indicator flag, a column that literally states sensor generation 1 for the first 3 years, and then switches to sensor generation 2.
The machine learning model will interpret that mechanical baseline shift as a physical change in the river. It will learn the signature of the new laser and mistake it for a permanent change in the watershed's sediment load.
You have to explicitly document the tool, not just what the tool is looking at. If we connect this to the bigger picture, it underscores how deeply vulnerable the data is to the context of its collection.
But unit harmonization and batch effects are just the prelude, right? The true peril lies in dataset fusion, the mechanical act of joining tables.
Yes. Slide 8 of the source material delivers a phrase that should be framed on the wall of every data scientist. Joins create claims.
Joins create claims. I find that phrasing brilliant. In software engineering, joining is just the mechanical syntax, the SQL or pandas command, used to stitch two tables together by matching a common thread, like a timestamp.
It is viewed as a purely clerical operation.
But the guide forces us to realize the immense scientific weight of that syntax. When you join a massive rainfall dataset from a weather station on the nearby mountain to your localized water quality dataset in the valley, you are not just organizing files.
No, you are fundamentally asserting a causal hypothesis. By placing the rainfall volume on the exact same row adjacent to the river's turbidity reading, you are mathematically asserting that the rain from that specific station directly contextualizes, influences, or physically causes the mud in that specific river at that specific time.
You are hard-coding a physical theory of cause and effect directly into the architecture of the spreadsheet.
And because that hypothesis is hard-coded so deeply into the structure, if the join mechanics are flawed, the resulting hypothesis is violently distorted.
The guide breaks down the common failure modes of joining data, and they are terrifying in their simplicity. The first is time zone mismatches.
It sounds so mundane, you forget to check daylight savings.
But walk through how that seemingly clerical error propagates into an algorithmic hallucination.
Let's say your in-stream water sensor operates on local daylight savings time, recording the exact moment the river crests during a storm. But you download the precipitation data from a federal weather API that inherently outputs in UTC-coordinated universal time.
Which is offset by several hours.
Right. And you execute the join based on the raw timestamps without harmonizing the time zones.
What does the resulting data frame look like to the model?
Well, you have just shifted the rainstorm backward in time relative to the river. The model reads the joined rows and sees that the river violently flooded, the turbidity spiked, the flow rate quadrupled, and then 3 hours later, the rain finally started falling.
You have mathematically broken the space-time continuum of the watershed.
Exactly. If you feed that joined data into a predictive neural network, the network will struggle to map the causality. It might conclude that river flooding actually causes rain, or it might just dismiss the rainfall data entirely as non-predictive noise because the temporal relationship is scrambled.
Another major failure mode highlighted by the guide is the nearest neighbor join across dangerously long time gaps.
This one is insidious.
Let's set the scene for this one. How does a nearest neighbor join physically fail?
Imagine you physically wade into the river and pull a water chemistry sample at precisely noon on a Tuesday. The sun is beating down, the water is warm, you take that data back to the lab, and you want to join it to the local air temperature.
Okay, so you write a script that looks at the weather station dataset and says, find the temperature reading closest in time to my Tuesday noon sample.
A standard nearest neighbor function. But what the script doesn't tell you is that the local weather station was struck by lightning on Sunday and went completely offline for maintenance. The absolute closest air temperature reading it has in its database is from 2:00 a.m. on Monday morning.
The implications of that.
The nearest neighbor function doesn't care about the physics. It executes the logic perfectly. It grabs that 2:00 a.m. Monday reading, let's say it was a freezing 34 degrees Fahrenheit, and seamlessly glues it onto your Tuesday noon row.
Suddenly, your sun-baked, warm water physical sample is inextricably linked to a freezing midnight air temperature from 34 hours prior.
And the machine learning model has absolutely no idea. It doesn't know the station was broken. It just looks at the row, blindly accepts the association, and learns a completely psychotic relationship between air temperature and water chemistry.
It will start predicting summer algal blooms in near-freezing conditions.
This is why you must set maximum tolerance windows for joins. You have to tell the code, find the nearest reading, but if it is more than 2 hours away, reject the match and leave it blank. You must enforce physical constraints on the software.
The guide highlights one more critical join failure: the many-to-one inflation of rows. This is insidious because it artificially manufactures data.
It occurs when you merge datasets that were sampled at fundamentally different frequencies. Let's say your physical water sample is drawn only once per day at 8 a.m., but you are joining it to a high-tech weather station that records temperature and pressure every 15 minutes.
That's 96 weather readings for every single day.
If you execute a standard left join improperly, the SQL logic will take your single physical 8.0 m water sample, and it will literally duplicate it 96 times to match every single 15-minute weather reading for that date.
So the physical reality is that you went to the river exactly one time. The mathematical reality you just handed the model is that you possess 96 identical, perfectly stable, unchanging water samples stretching from midnight to midnight.
You have hallucinated data volume. You artificially inflated your statistical power by a factor of 96. If you train a random forest on that inflated data frame, it will look at those 96 identical rows and calculate a variance of 0. It will report back to you with astronomically high confidence in its predictions.
Because it thinks it has witnessed the exact same phenomenon 96 times with 0 deviation?
Precisely. The p-values will look spectacular, the accuracy metric will be flawless, but it is a statistical mirage built entirely on a syntax error during the join.
This is why the guide provides a cardinal, non-negotiable rule for dataset fusion. Always count what didn't match.
Always count what didn't match. You have to look at the cutting room floor, you have to inspect the rows that failed to merge.
The forensics and the drop data. If you start with 1,000 physical water samples, and after running your join script to add the weather data, you notice your data frame only has 850 rows left, you cannot just shrug and run the model.
You are ethically and scientifically obligated to investigate those 150 missing rows because
Right.
they rarely drop out purely by chance.
Exactly. Why did they fail to match? Did a field tech misspell the site ID? Was there a time zone bug?
Or, far more critically, did those 150 samples all happen to occur during the massive hurricane last year, the exact same hurricane that knocked the weather station offline?
If you don't check the unmatched rows, you might be systematically deleting the single most important extreme event data in your entire decadal study, all without triggering a single software error.
It is the ultimate scientific arranged marriage. You are taking two totally distinct physical lives. The life of the anemometer spinning on the mountain peak and the life of the turbidity probe buried in the mud of the valley.
And you are forcefully confining them together in the rigid architecture of a single spreadsheet.
If their temporal realities, their chemical units, or their physical context do not perfectly meticulously align, the resulting relationship will be a disastrous misunderstanding that the algorithm will confidently interpret as fundamental truth.
The joins dictate the absolute boundaries of the reality your model is allowed to perceive. The algorithm cannot go outside and look at the river. It can only see the spreadsheet. If the join is physically flawed, the model's reality is permanently flawed.
That is the whole crux of it right there.
So what does this all mean? We have walked through an absolute gauntlet of data architecture today.
We really have.
We've seen how a single text string can imprison the temporal and spatial dimensions of an experiment. We've mapped out how prematurely averaging replicates destroys the footprint of measurement uncertainty.
We've learned that a blank cell is a physical mystery to be solved, and that a zero in place of a detection limit is a dangerous mathematical lie.
We've engineered features that literally teach an algorithm the memory and gravity of a watershed, and we've navigated the treacherous, illusion-filled waters of forcing different datasets to talk to each other.
The synthesis of all these intricate mechanisms, the ultimate lesson of the Facilitator Guide, is a profound paradigm shift in how we view our role as analysts.
The guide states that after surviving this pre-processing gauntlet, you should never, ever stand up in a scientific meeting or a boardroom and declare, "My data is clean."
Because clean is a myth.
Clean implies that the data is now a perfect, untainted, passive mirror of reality. It implies an absence of human interference.
But as we've exhaustively detailed today, preprocessing is not cleaning. It is a dense, highly active series of subjective interventions. It is a cascade of choices.
So what is the honest alternative? If we can't say it's clean, what do we say?
Instead of claiming cleanliness, you must explicitly state the assumptions you mathematically embedded into the data to force it into this state. You must articulate the uncertainties that remain, the blurry footprints you couldn't perfectly resolve.
But most critically, you must define what specific physical analyses are now strictly permitted and which are forbidden.
Right. Because of the specific choices we made. Because we chose to substitute our below detection limits with a fractional value, and because we detrended the sensor drift, we have explicitly bounded the capability of the model.
Maybe we are now highly qualified to describe decadal long-term nutrient trends, but because of those exact same pre-processing choices, we are mathematically, structurally forbidden from predicting acute, extreme flash flood events.
The architecture of the input dictates the validity of the output. The guide closes with a line that strips away any remaining illusion. Every pre-processing choice is a contract with reality. If it isn't documented in the methods section, it does not exist. Models are no longer excuses, they are commitments.
You can no longer shrug and blame the black box algorithm if the prediction fails to match the physical river. The neural network just faithfully digested the exact physical worldview you handed it during pre-processing.
It really puts the responsibility back on the human.
Which leaves me, and hopefully you listening right now, with a genuinely lingering, somewhat provocative thought to mull over. We've established today that every single step of preparing a data set, from deciding the fate of a blank cell, to mathematically translating the residence time of a stream, to deciding exactly how to join a rain gauge to a water probe.
Every single keystroke encodes a human hypothesis.
It is an active human choice. If that is fundamentally true, is there really any such thing as raw, objective data once a physical measurement crosses the threshold into a computer?
Or is every single data set, at its very core, simply a mathematical reflection of the scientist's own worldview?
The next time you open up a pristine, perfectly aligned, highly formatted Excel spreadsheet, remember that you are not looking at a sterile laboratory. You are looking at a heavily curated, painstakingly altered crime scene.
And it is entirely up to you to figure out exactly which footprints the last person decided to sweep away.
Thank you so much for joining us on this deep dive into the muddy reality of environmental data. Go look at your spreadsheets a little differently tomorrow.